Welcome everyone to another evening with the Berlin Functional Programming Group. I cannot overstate how excited I am for this evening's talk with Hillel Wayne. Hillel Wayne is the person I have known for a long time as the TLA plus guy. I hope he's not offended by that moniker. I've seen him posting about TLA plus for a long time. I've seen his talks. I've been wanting to have him. I think I probably reached out months ago to arrange this. I think this is an extremely exciting technology. I would even want to try and push this at work myself, which I can't say for every functional programming topic. And I also think that he is a fantastic salesman for this idea and for the benefits that formal methods can bring to real production systems. So it's not just theoretical and interesting for its own sake, but has actual practical value. And I think I don't know what to expect tonight, but I think he's going to demonstrate that actual case for us. And you're all going to be sold on the promises of formal methods and run to implement this in your workplaces. At least I'm hoping I can make this happen for myself. I'm really looking forward to seeing what Hillel has for us. And I'm so delighted and grateful that he's willing to join us virtually in Berlin tonight from Chicago. Thank you so much for being here, Hillel. I'm going to switch it over to you now.
Okay, thank you for having me. Can you all see me? Can you all see my screen? Can you all see the talk?
Yep, looks good. Oh, and I just want to ask anybody who has questions, please save your questions for the end, but feel free to type them into chat if you like, and then we will just catch up with all of those later.
Okay. Hi, everybody. Thank you so much for coming to this talk. As introduced, my name is Hillel Wayne, and I'm going to be talking to you about designing distributed systems with TLA+, aka, this clicker, aka, everything about distributed systems is terrible, aka, Waterfall, good actually. We're going to be covering what we mean by a distributed system, why they're so terrible, why most of our tools don't work, or at least only work partially, and how TLA Plus can help. Not fix things, help. I do not believe in snake oil. Couple of disclaimers before we begin. One, I do this professionally. This is like 30% a sales pitch. So if that is a problem for you, just letting you know now. Two, Zoom talks, always horrible. I apologize for this in advance. I'm going to be doing the best I can to adapt this talk for a remote talk, but there's probably going to be some issues. And then three, this talk involves a worked out specification as well as a lot of additional resources. Additionally, I've given this talk before and I've gotten questions. And what I do is I put the spec and the references as well as all the questions at this link. So if you have like questions, I will also be taking the ones that you give me and putting them online too here. And with that, let's actually begin. What do we mean by distributed system? Now, I've been to a lot of conferences and everybody who talks about distributed systems has to use this quote by Leslie Lamport. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Everybody uses that quote. It's kind of a meme at this point. And I'm honestly not a huge fan of this because what it does is it sort of focuses the dissim on the computer. It doesn't really talk about what this is as an abstract concept. And to show you why those two are actually different, I want to present a quick thought exercise. Here is a typical distributed system. We have two computers and a server, say a database. Each computer pulls the information from the server and then assigns it to a variable and then updates the server value based on the temporary variable. This, everybody agrees, is a dissim. On the other hand, if I now instead use the following, where I have, instead of two computers and a server, I have two threads in a file on the same computer, but I do the same logic, people say this isn't a dissim. Even though I'm doing the same logic here, one is a dissim and one's not. Why is that? Now, people give a lot of like differences for why, but it really boils down to this one thing, history. If you look at the early work done on threading systems, like the work by Dijkstra, Dekker, etc., they actually treat them in much the same way that we treat dissims now. They're worried about the same kinds of issues, the same kinds of race conditions. They're even worried about the same kinds of partial failure. A common thing you see appear in the literature is what happens if the thread scheduler just never gets back to a sleeping thread. Essentially, a lot of the same abstractions that were used to study threads later were used to study disk-sims at an abstract level. We're essentially using the same ideas to model both of them. The only reason why we don't consider threads disk-sims now is because these days we have much better hardware that can enforce local invariants, things like compare and swap. We've essentially used technology to undistribute them. This isn't the same thing, of course, with disk-sims. We haven't yet gotten to that point, so we have all the same issues we used to have with threads. Now, this idea of seeing these both as like projections of the same abstract idea is one that I like a lot, and it sort of leads to abstract definitions of what we mean by disk-sim. Specifically, we can model a distributed system as 3 properties. We have multiple agents acting independently. They have global properties we want to enforce between all of them. If we don't have global properties, if we only care about the local properties of each, it might be distributed, but it's not a system. We just don't care how the things interact. And critically, we also have localized information. What that means is that while there is emergent global properties, we care about them all sharing, each individual agent only sees one small slice of the big picture. If they want to get information from other agents, they have to actually ask for that. Now, people also add a 4th property, which is partial failure. Some agents are allowed to fail while the entire system still works. This we can actually talk about as a consequence of the original first 3, which is why I don't see it as critical, but it is still one of the most fundamental practical issues of these systems. And all of these properties by themselves are enough to sort of make disk-sims such a terrible problem. To see why, we need to introduce 2 concepts, state spaces and behavior sets. To introduce them, let's talk about one of the emergent properties of multiple agents, concurrency. Concurrency is the ability for multiple agents to run in different orders. They're all running simultaneously, but multiple things can happen based on the interleavings. And this affects the possible things the system can do. Another example. We have 2 agents sharing some global value, x. One agent increments x, one agent doubles it. We can assume that these are atomic. The first agent will always run this in exactly 1 step. The second agent will double in 1 step. But they're also concurrent, which means they can run in any order. We can have either the first agent run and then the second, or the second then the first. How many possible n values of x can we have? I'll give you all a couple seconds to think about that. Can I also introduce some laser pointer so I can have this laser pointer sick and then cool. Okay. So most of you, I imagine, probably got there's 2 possible n values of x. Either we double and then increment and x is 3, or we increment and then double and x is 4. Now, notably, what's interesting here is that even though we have 2 possible end states, each one also corresponds to an intermediate state. There is the state where one agent has run, but the other one has not. We call these states, and together they form the state space. Additionally, we can talk about the paths followed through. We either go x equals 1, 2, 3, or 1, 2, 4. These are what we call behaviors. And the behavior set is size 2. So 5 states, 2 behaviors. This is a pretty practical model. We can keep this all in our head. But as we make systems more complicated, introduce even slightly more concurrency, things start to get a bit out of hand. Now, let's say that instead of each agent having 1 step, they have 2. They first assign to a local variable, and then they change the value of the global. We also allow these to be nonatomic, meaning the first agent can run this step, and then the first agent can run all of its steps, and the second agent can run its second step. Interruptions are allowed to happen. Before we had 5 states, 2 behaviors. How many states and behaviors do we have now? Again, I'll give you a second to try to work through it. So instead of 5 states, we now have 13. And instead of 2 behaviors, we now have 6. In fact, if we added a third agent, we could potentially have up to, not necessarily always, but we could have up to 540 distinct states. Essentially, concurrency leads to what's called state space explosion. Even a small amount of things being allowed to interleave lead to lots and lots and lots of possible unique states. This is really one of the most common properties of disk-sims. The number of states, the state space grows fast. Now, that's only concurrency. That's only one part of this entire deal. And it's only really the state space. I haven't even talked about the behavior set yet. Both of these can really are affected by what we call nondeterminism. The original example I gave of the two workers was deterministic. It was concurrent but deterministic. Each agent always did exactly one thing at one time. While we can have multiple possible interleavings, each agent was sequential. That really doesn't model the real world very well, because imagine we instead had workers that took user input. The user could input what value they wanted the worker to act on. While the individual thing that happens based on the input is deterministic, the user's choice is non-deterministic. We can't force it to be exactly one thing. Additionally, not all agents will do their steps. Some of them will crash, that partial failure I talked about. Non-determinism is where we say that while we have a single step, one of multiple things can happen in that step. Either we increment x by 1 or by 2, or the thing crashes entirely. And this does nasty things to the state space, but it can also do very, very nasty things to the behavior set. New example, 2 agents. Global property x is 0. One agent decrements x as long as it's less than 6. Other one increments x, sorry. First one decrements x as long as it's greater than 0. Second one increments x if it's less than 6. 7 possible states. If we only look at behaviors that are 5 steps long, we have 16 5-step behaviors. Admit. Now let's add a small amount of non-determinism. Instead of the agent being allowed to increment x by 1, if it's less than 6, it can increment by x by 1, or if it's less than 5, it can increment x by 2. So noticeably, if x is, say, for example, 3, we are allowed to either decrement it to 2, or increment it to 4, or increment it to 5. This doesn't change the state space at all. We still have 7 states, but the behaviors change a lot. Instead of 16 5-step behaviors, we now have 113. Essentially, any possible path through the state space following the edges between states, the state graph, leads to a distinct behavior. And because there are multiple paths through a graph, even with like a few nodes, the number of behaviors in the behavior set grows very, very fast. Quick off-topic thing I just want to clarify now. I'm using behavior set versus state space because the state space implies directionality and metrics. Essentially, that's where the entire graph comes in. With behavior sets, I don't think anybody's really modeled the ability to transition between behaviors. Anyway, that's more of a tangent here, just something I find interesting, letting my own like nerdery dive, like go through my professionalism. Any case, the reason we have to talk about both state space and behavior set is because both of them can lead to problems in our system. We sort of have an intuitive model that states can be bad. There are states that we might not want to be possible. Imagine that this was the state space of a database. If this state is one where we're violating a database constraint, we have a problem. We do not want that state to be reachable in our state space. But what people are less likely to realize is that there's also behaviors that are invalid, behaviors we want to not exist in our behavior set. Imagine, for example, eventual consistency. There is a point where we want to commit the data but haven't yet. Because that is a valid state, there might be a path through the state space where we intend to commit data but never actually do. Each of those states, because we can always commit data in the future, must be considered valid. But if we never end up committing data, though we've passed only through valid states, we have an invalid behavior. Both states and behaviors may be problematic. Now, where this sort of transmits from interesting properties of dissims to them being fully terrible is the scale we work at. Dissims are unique in that a single invalid behavior or state is too much of a problem for our system. It is something we do not want and want to rule out. And this is, again, because we run at scale. Imagine we have 1 billion, imagine we have a system where 1 in a billion events causes a critical outage. So 1 in a billion, if we run 1 event a second, that would be 32 years before we see anything. Now imagine that we're running at a scale where we only see 100 events a second. This is actually not that large for a dissim. I've worked on small ones that are larger, honestly. How long will it be before we see the first critical outage? Three months. At the same rate that US businesses file their quarterly taxes, they have critical outages. Or more precisely, over a long enough time, a system will do everything. It will see every possible state in the state space, and visit every possible behavior in the behavior set. You might also know this as Murphy's Law. Anything that can go wrong will go wrong. And this is why dissims are terrible. Now, I'm not the first person to notice this. And a lot of people have wanted to make these systems less terrible, and there are lots of solutions. Some of these solutions are so common we don't even think about them anymore. Those are things like compare and swap and transactions. There's things that are widely used by a lot of different languages, things like locks and promises and async await patterns. Then there's stuff that's on the very cutting edge of programming language theory, things like software transactional memory or supervisor trees or like full-on actor models. Now, don't get me wrong, a lot of these are very good. And I do use a lot of these, and I think these are all great tools. But everything listed here has one problem in common between all of them. Everything listed here is code. It is something that when you take it and use it, cuts out parts of the state space. Hopefully, parts of the state space that include invalid states or lead to invalid behaviors. But we don't know that for certain. All we've known is that we've pruned the state space somewhere. If the invalid state is here, we still have a problem. If this is the invalid behavior, we still have a problem. See, fundamentally it boils down to this. The state space is a consequence of our design. Code is not design. Code can't be designed. Code isn't supposed to be designed. We can't, in the end, solve a design problem, the state space and behavior set caused by the dissem, using code alone. We need some sort of means of dealing with it via design. Now, the reason why we use a code solutions, not design solutions, is because, unfortunately, most designs are untestable. When people think of designs, they think of things like flowcharts or like UML diagrams or sequence diagrams, things that you can draw and you can study as a human, but not things that you can actually formally, like machine verify are actually correct. If I show you a bunch of files saying, hey, I drew a design, I thought about it really hard, it should probably work, that isn't very convincing. Code, at least, while it might not actually be effective for understanding the state space, is at least testable. We can use programs to make sure our code is correct. Now, the alternative would be to find some way of combining both of these, creating designs that are testable. This is actually a field of study. This is what we call formal specification. Specification for design, and formal being a design that is so precise it is machine checkable. There are many tools in this space. While it's not very mainstream, it is still exists, and we've seen a lot of success with different tools. I use a lot of different ones. I think a lot of them are great. I'm going to focus on only one, the one that has shown to be extremely effective for concurrency and has also seen a lot of real-world use in all sorts of companies. I'm referring, of course, to TLA plus the temporal logic of actions. This was invented by Leslie Lamport, a giant in the dissim field, as well as the inventor of LaTeX, whose idea was that by sort of leveraging ideas from mathematical notation, we can express things at a much higher level than we can with programming notations. TLA plus is designed around this. To give some examples of what I mean, in a programming language, we might initialize a queue to be an empty array. In TLA plus, we're talking about the entire state space. So we can say multiple possible initial states are valid. Maybe the queue starts with no messages, or maybe it starts with 5. And instead of talking about what the system does, we talk about how it can evolve. In a programming language, I can say, add a message to the queue. Get the result. If it's a success, do this. If it's a failure, do this. But I don't know whether a given message will succeed or fail. I can only talk about how we react to that. In TLA plus, though, as a model, I control the entire world. I can say it is non-deterministically possible that we successfully add a message to the queue, or we fail and nothing happens, or we try and we accidentally add the message twice. This gives us the ability to talk about the entire design, both what should work, what could fail, and how we react to what could fail, in addition to just how we react. Once we have that, we can then talk about the properties of the spec. We can talk about properties that we have to guarantee for all states. For example, that in every state there must exist a server that's online. And then uniquely, compared to programming, we can also talk about properties on entire behaviors. We can say in every behavior, there must be a point where every server is online. So every state, there must be at least one server, and in every behavior, there must be a state where every server is online. Then once we have specs and properties, we can then test them. TLA Plus comes with what's called a model checker, TLC, which explores the entire state space and sees if any states or any behaviors violates the properties we have. If it finds one, it then gives us what's called an error trace, showing exactly how we go from the start to the error. Now, I believe like a lot of the people here sort of already know the work I do. So you've already might have seen this already. I find that when I give this talk, a lot of people have never encountered anything like this before. And because of that, I like to give people a demo. But I'm really not a fan of most of the canonical demos. They're usually either things like simple hour clocks or water crossing puzzles, or they're incredibly complex distributed algorithms like Paxos or Raft. Neither one is what most programmers are doing day to day. So with that in mind, I tried to craft an example that's a little bit more representative of what a business might actually want to use this for. In this case, an ETL, any sort of data pipeline. We have a user that is creating uploads. I don't care what kind of upload. It could be images, it could be like videos, it could be CSV files. And I want that to be transferred by a worker into content. I don't care what kind of content. It could be transcribing audio, it could be producing thumbnails from images, it could be producing like articles from like text files. All I care is that we add uploads and we produce content at a high level. Users are allowed to delete uploads, in which case the server must also delete the content. And finally, the user might want to edit an upload, make some sort of change, in which case the worker must take down the old version of the content and put up the new version. Now, because we expect to have multiple users, this needs to scale. We need to have multiple workers able to process these things. And I also want this to all be asynchronous, meaning that instead of it being directly the user creates the upload and they wait for the worker to finish, the user can create the upload and do something else. That means that every time we create or edit or delete, we're putting a message onto a perfect queue. We will assume the queue is a perfect FIFO, first in, first out queue, never drops messages, never reorders messages, never duplicates them. And then they are pulled by the workers and then processed. I want to model the system at a high level with TLA+. And then I want to sort of show how we can take properties and see how versions of the system can break these properties. A couple of caveats though before I begin. First of all, and I really do need to emphasize this, specs do not check code. We are working entirely on the design. I do not promise snake oil. I am not promising something that replaces your ability to test or use type systems or just be a good engineer. This is a distinct additional tool in the toolbox. It does not replace these things. And second, TLA Plus uses a very idiosyncratic syntax, which people can learn pretty quickly, but you are not here to learn TLA Plus, you're here to hear me pitch it. So to make things a bit more understandable, I have transformed all of the syntax to look more Pythonic. I have not changed any of the structure. I have not changed any of the flow. I have just changed the way the keywords look. You can see the original spec again at this site. Okay. Step one, extend imports. We also have what we call parameters, things that we can tweak per run of our model checker. How many users we have, how many workers we have, and then this null thing I'm going to skip. We have our variables. We have a set of uploads and a set of content. We have a queue that is a list. And then because we don't really care about what properties we don't really care very much about sort of the individual properties of uploads and content, just they exist, we use an ID to distinguish them. And the ID will just be a number. So each piece of content that's distinct will have a different ID. Sending a message is a function that takes the queue and appends the message we want to send, which will just be a dict containing the ID of the upload we're working on and the action, which will be create, edit, or destroy. Now we have the system we want to model. There are two agents here, the person and the worker. In a program, I could express how we react to the person's input, and I can react what the worker should do. I couldn't say what the person would do. In TLA Plus, though, I can treat them as just any other agent. Now, the person is allowed to create, edit, or delete, but we don't know which one they'll do, and we don't know in what order they'll do them. They could create something, they could create 5 pieces of content and then delete 4 of them, or they could create one, edit it 3 times, create another one, delete the first. or they could just create, never bother to edit or delete. We want to allow all these to be possibilities. We do this with an either statement, saying they either create or edit or delete. The model checker, when seeing this, will create 3 separate branches, one where they do each one of those 3 things every single time it sees this. So basically, if we run the loop twice, it'll create 9 possible branches: create, edit, delete, and then create, edit, delete. Create, we first create a temporary variable defining what an upload looks like. I define it as who it's from, the version it is, which starts at 1, and the ID, distinguishing unique pieces of content. We add an upload to we add it to the upload set, and then we send a message saying, hey, create this corresponding piece of content. Then we increment the ID, so the next piece of content will have a unique thing. Delete would work analogously, where we just remove the delete and we send a message, except just like overall choice, this is non-deterministic. If the user wants to create, if the user has created 2 or 3 pieces of content, they should be allowed to choose which one they want to delete. So we can say that the delete is in the set of uploads. And here, if there's, say, 3 elements, we'll branch 3 times, 1 for each possibility. Edit uses both of these. We choose non-deterministically which upload they want to edit, and then we produce deterministically what the edit looks like. It's the same user, same ID, and we just bump the version number. Again, that's because we've abstracted out the actual content of these uploads and content of the uploads and content. We just care that they're distinct in the version they're on. Then we remove the old version from the uploads, add the new version, and send a message saying, hey, edit this ID. And with that, we're done with the person. We now have fully modeled what the person can do. They can create, they can edit, they can delete, they can do it however many times they want. Now for the worker. The worker is going to wait for the queue to be non-empty, pop the head of the queue, and then process it. For processing it, they can create. If the message says create, they do a create action. If it's edit, they do this edit stuff. And if it's delete, they delete it. If we get something else, there's something that's gone horribly wrong, and we just assert false to break out. Now, these things, these green things, are labels. They represent the points of atomicity. What this means is that after the worker has received the message and starts the create action, other workers can do other things. The user can do other things. So the user can upload something, and then the worker can receive the message saying, hey, create this. And then before the worker has created it, the user can create something else. To make things interesting, I've made edit nonatomic. We have to do this in 2 steps. First, we start the edit where we take down the old piece of content, and then we push the new piece of content corresponding to the edit. In any case, for creation, we select the upload that matches the ID of the message. Then we pick that upload and we add it to the content set. Very simple. Delete works analogously. So we just remove the corresponding upload from the content set. We're again using the same sort of fields. We're just distinguishing whether you're upload or content based on which set you're in. Edit, because it has to happen in 2 steps, what we do is we first remove it in the first step from the content set, the existing value, and then we basically store what the upload is going to be in a local variable here. So we basically look at the upload, we say, okay, we're going to store that locally. We're going to start producing the corresponding edit. We remove the old version, and then we push the new version. And that's it. That now represents the worker. We've now modeled everything the worker can do. Now I can start talking about properties, what I actually want this spec to guarantee, and that we can check. The first thing isn't actually a property at all. It's just comprehensiveness. Is my spec unambiguous? Does it describe that something should happen in every case? Is it possible to reach a situation where the spec doesn't describe what should happen next? In order to sort of test this, I just have to inject a couple of parameters. I'm going to say there is 1 worker and 1 user. Then I load this up in the IDE called the toolbox, and I run the model checker on it, which looks like this. So this popped up on the side. That means we have a bug. It has managed to find a trace where it is not sure what should happen next, and we have ambiguity, and we are not comprehensive. Top here says the error. Bottom here is the trace, the steps that have to happen to cause this. What happens is we first create an upload. The worker receives the basic, and we send a message onto the message queue. Then before the worker receives the message, we delete the upload. The worker receives the create 1 message, but there is no corresponding upload. It cannot find the upload corresponding because it was already deleted. We have not specified what should happen if the worker tries to find a piece of content that doesn't exist. Now, one simple thing I could do is I can say only do this entire create song and dance if the upload exists. If the upload doesn't exist, then what must have happened is it was deleted beforehand and we can just safely ignore things. I will shorten it to this for now. If I do this and do the corresponding changes to edit and delete, we no longer have an issue. This now works, and I can start talking about actual interesting properties. Now, in the real world spec, I'd have a lot of different properties. I'd have type invariance, I'd have duplication invariance. Here, I'm just going to focus on one. I'm going to focus on one that's a behavior property because I talked about how interesting those were before. I'm going to call this no orphan content. Every piece of content must have an identical upload. In other words, we cannot have content that is out of sync inversion-wise with the uploads, and we can't have content that's left over after the upload is deleted. Now, this isn't actually a property on the state space. To see why, imagine if I've uploaded something, so there's now both an upload, we create the content, and then I immediately delete the upload. There is, in that exact moment, these are no longer true. We no longer have content, we no longer have an upload matching this piece of content. This is only true in the long run. It is true over the entire behavior. So I add this thing saying, always eventually. There must always be a point in the behavior where these two things are in sync. It can be locally wrong for a few states, but we must bring them back in sync. Now, obviously, I wouldn't be introducing this property if it wasn't broken. And it's broken for a pretty interesting reason, stuttering. That corresponds to the following. User creates an upload. We put the message. The worker receives the create message. It creates the corresponding piece of content. The user deletes the upload. Now we're out of sync. We have a content without a corresponding upload. The worker receives the delete message saying delete this piece of content. Then it crashes. I talked about partial failure being one of the big problems of dissens, not necessarily a fundamental property of it, but one of the big problems. TLA plus assumes that at any point, anything can crash. Anything can just simply stop making progress. We have to be explicit about whether things can crash or not. Now, I might want to actually build this in as logic. For this demo, I'll simply say the worker cannot crash. It is what we call a fair process. I'm not going to make the same change to the user, though, because I cannot guarantee the user doesn't crash. The user can at any point stand up, decide, I hate this, and go outside. They'll have to put on a mask and just be outside for a short time, but they couldn't just walk away. In any case, if I do this, we've now fixed it. We now know no orphan content is satisfied for one worker and one user. But what if I want to scale it up? What if instead of one worker, I want to have 3? Testing this in a program would be very difficult. I'd have to very carefully build a test rig that can simulate all possible interactions and all possible ways that all the interleavings can happen, which is one of the reasons why people who do this are actually well-paid consultants. In TLA Plus, though, I just changed the parameters. I simply say instead of having 1 worker, you have 2. Now, I think it's pretty clear that this isn't going to be satisfied either. I wouldn't be bringing this up if there wasn't a trap here. I'm going to instead ask you all a different question. How many steps are required for this to break? How many steps do we have to have happen in just the right order for us to no longer have no orphan content be satisfied? Man, I miss going outside. Stupid pandemic, stupid winter. Okay, who guessed 15? 15 things have to happen in just the right order, with just the right setup, with just the right nondeterminism for us to have our property be violated. Not something you'd easily find in a test. It corresponds to the following. Create an upload. Create the content. We edit the upload. The first worker receives the edit command and takes the content down. The user then deletes the upload. So now there's no longer an upload. We push a delete message to the queue. The second worker receives the delete message, sees that there's no corresponding content, and basically just ignores it. Then the first worker pushes the edit. And now we have content on version 2, no upload, they're out of sync. I can fix this by saying, okay, clearly we've had some content that doesn't have a corresponding upload. We probably need a nightly job that just goes through, sees if there's any leftover uploads, leftover content, and just deletes them. So if there's any content that doesn't have a matching upload ID, just kill the content. And this will fix the error. We will no longer have a 15-step error. Instead, we have a 16-step one. We have a 16-step error that follows a completely different error path. Create an upload, worker creates the content, worker edits it, the first worker pulls it down and is about to upload version 2. The user edits it again. The second worker is supposed to basically sync it to version 3. It sees the content doesn't exist. It edits this. It sees the content doesn't exist and stops. Then the first worker pushes the edit. So now we have the content, the upload on version 3, the content on version 2, they're out of sync. They're never brought back into sync. To fix this, we can be a bit smarter with our, give a second. To fix this, we have to be a bit smarter with our edit logic. We first check to see if we'll be uploading a version that's out of date. If we're going to be editing and uploading some content that's already an earlier version than the upload, we just stop and restart. And this will fix the error. This will mean that we no longer have any errors at all. We now have guaranteed that between these two changes, no orphan content is now satisfied for 2 workers and 1 user. But notice something pretty interesting. I made 2 changes and one of them didn't fix things. I made the change to add the nightly batch job and that didn't fix the error. We still had an error that violated no orphan content. Was that necessary in the first place, or is that just extraneous complexity? If this was code, that would be very hard for me to tell. It would have taken me a long time to get to this place. It's hard to find these kinds of bugs. It would probably be a lot of changes to integrate both of them. It would be too difficult for me to take out the batch job, see if the error reoccurs, and then put it back. In TLA Plus, though, that is literally a 30-second change. Just remove the process, rerun the model check, see it fails. We actually need both. We need both smarter edit logic and the batch job to make sure we have satisfied no orphan content. I think it's pretty cool. That gives us the ability to look for incredibly deep, complicated errors very, very quickly. Of course, that's a demo. How does this work in the real world? For this next section, I want to quickly talk about some of the real-world use cases we've seen. TLA Plus has actually been around for almost 30 years now. It originally came out, I believe, in 1994. But it only started seeing some mainstream adoption with this, the use of formal methods in Amazon Web Services. This was a 2014 paper, and I believe was reproduced in ACM in 2016. And what it was them talking about how they use TLA Plus to verify components of AWS. Specifically, and they talk about it here, S3 and DynamoDB with a few other uses later. They said that this cut a lot of time off of their schedules. It ended up saving them a lot of time and worker money. Additionally, it found some truly extraordinarily complex bugs. One of them had passed their code review, all their testing, all their design review, all their linting, all of their other systems, and led to lost data in DynamoDB. The end result bug took 35 steps to appear. If you thought 16 steps was bad, 35 is a whole lot worse. And this was actually, I'd say, the breaking point for the open the floodgates. This was when people started actually experimenting with this in the real world. This paper inspired a lot of people to start looking into this. I was one of those people. At the time that I read this paper in late 2016, I was working at Espark Learning, which is a small educational software company that makes an iPad app for elementary schools. We had a total of 10 engineers at the time. Very, very far from what Amazon's doing. Very, very much smaller company. Our system was what we called accidentally distributed. It turns out that we had interactions between our software and Apple software and Apple's other software and the school's mobile device managers and the school's servers and all the iPads themselves. And we saw all sorts of crazy distributed system bugs start appearing here. We used a lot of techniques to try to deal with this, of course, like code review, TDD, like better systems, microservices, and a lot of them sort of helped, but none of them really killed a lot of these things. At one point, we decided to start trying TLA Plus, and we're astounded at how successful it was. It found a bunch of really nasty bugs we'd walked right into with our new systems. It we even started seeing, and this was the most surprising to me, we even started seeing people talk, like the school admins start telling us how much more robust our systems seemed. After we started applying TLA Plus, they noticed the improvement in quality when things would go down less often, have weird behaviors less often. And that was what inspired me as a person who was doing something so far from what Amazon was doing, just in a small user-facing app company, and found it so useful. That's what inspired me to first write a tutorial and then start giving talks on this, and then a book, and then start eventually consulting with workshops. It's what convinced me that this is really powerful stuff. And a lot of the reason why people don't use it are more circumstantial than essential to the actual technique. So in conclusion, distributed systems, terrible. Specification helps, doesn't fix things. Again, no snake oil, but helps. TLA Plus, kind of neat. I don't expect anybody's going to rush outside and start applying TLA Plus right now from this. That's not how things work. But hopefully I've gotten some of you more interested in trying it out, at least. So I'd like to conclude by talking about some resources to start. First one, as mentioned, I wrote a book on this, Practical TLA Plus. It's designed for people who are interested in using this in their businesses, but don't have a mathematical background. With that in mind, it focuses on practical examples, things like MapReduce, business logic. There's like one long piece where I analyze like a library, like reservation like system. It's available now at is.gd/PTLA plus. You can buy it, their ebook, PDF, whatever. If you want to go further than that, there's Specifying Systems by Leslie Lamport. This is more intermediate level and sort of assumes people have some background, but it's also the canonical text. It covers not just TLA plus, but also the theory behind it, how all this works as a mathematical formalism. He's also produced a video course that is available online at his site. Finally, you can just hire me. I do workshops, pretty intense 3-day workshops. One person once described it as the first corporate workshop they took that wasn't a complete waste of time. It's usually 2 days of like learning and then a day of applying it to actual business systems people have. And funnily enough, we find bugs in like that third day in their actual systems, which is kind of crazy. You can go onto the site, hillelwayne.com/consulting, or just talk to me afterwards. And really, that's all I have to say. Thank you so much for coming to this talk. I am now happy to answer any questions you have. Thank you.
Hey, thank you very much, Hillel. We have a few questions already. And I will just go through them one at a time, and also invite other people to ask questions. You can just say, I have a question, or if you can't unmute yourself, you can type your question and I will ask it for you. So first is, let me see, Artie. Artie, do you want to unmute and ask your question?
I can read the question too if he doesn't want to unmute. It's, is there a conceptual relationship between PBT and TLA plus? So by PBT, we mean property-based testing. That is where you have, instead of writing test case where you say 6 + 5 = 11, you instead say, for my adding thing, for any A plus B we add, it should give the same result as B plus A if we swap things around. And then we use what's called a test generator to generate, say, 10,000 integers and try them all randomly to see if any of them break that property. If you do that, you'd actually see if you're, say, running on C, it would say, hey, this is actually wrong. If we try int min, if you say like int max plus like -1, it gives a different result than like -1 plus int max. Probably not exactly. I think that's more of an associative thing, but you get the idea. So yeah, there's actually like been more and more crosstalk between like those two communities, because generally the people who are interested in either one tend to be interested in correctness techniques in general. I'd say the main difference is that property-based testing is much more focused on actually verifying code. So you actually have the code you want to test, and you're actually running tests against that code. TLA Plus and other kinds of formal specification tools are more on the design level. They can also afford to be more comprehensive because of that. Essentially, property test will always test things like randomly, but it will never be exhaustive. I know that, like, again, when I say those crosstalk, there have been features inspired in various property-based testing libraries that have been inspired by formal specification tools. And I know that some people in formal specification language are looking at trying to apply things like test shrinkage and like generators to make specification tools better. So they are conceptually somewhat similar, focus on very different things, and the communities are trying to learn from each other.
Thank you. And Milos has a few questions, I think, and Milos can unmute.
Hey, Hillel, here's Milos. Yeah, so my first question is, have you seen TLA Plus used in something other than distributed systems? I don't know if it makes sense, and not that it's, it's not enough.
So I have seen it used for sort of single threaded algorithms where people like have an algorithm where like they want to make sure the algorithm is correct for like all possible inputs. That's the thing I've seen it used for, and I've seen people like use it for. I don't like things like embedded hardware and like spin locks and stuff, things that basically involve concurrency that aren't full-on distributed systems. That said, TLA Plus is really designed about being really good for concurrent systems. And if you're not doing a concurrent system, it's not that it's bad, but it's that there's better tools. Like you could actually pull out like something like a theorem prover and actually like formally prove everything correct as opposed to using a model checker. So it's not that it's like not good for other things, it's that there are also better tools, and I don't like telling you to use a tool when there's like other options that might be more appropriate.
Okay, cool. And second question, after writing the TLA plus and moving on to the like what other programming language, do you ever get back to the TLA plus part, or is it like done and water?
It can go both ways actually, because I've seen what people do is that when they have systems they want to understand, they will actually model out in TLA plus to basically understand that system better. Or if they want to make a change, they will write the spec that models existing behavior and then modify the spec to represent the new behavior. There's actually one really hilarious high-profile case, not in TLA plus, but actually in Alloy, which is a different formal method that in Rackspace, where one person was trying to understand like one of the systems this way, and ended up finding a critical bug that had them force them to redo a year of work. I can link that talk afterwards if people want. It was at Strange Loop 2 years ago.
Okay, thank you.
Mm-hmm.
Thank you. Benedict has a question. Go ahead, Benedict.
Yeah, hi. Thank you for the talk. It was very exciting.
Glad you enjoyed.
How do you decide what level of abstraction you use in your TLA model? So what parts you abstract away, and because this seems to be a bit difficult to decide before you actually have your properties.
I'm going to give you the least fun answer imaginable, like the most infuriating answer. How do you do that for programs? Lots of experience.
Okay, yeah.
Like, let me put it this way. Like, the thing is, the difference is that with programs, like we have enough like knowledge of how it works to like be able to give like good guidelines. Like we know like, yeah, here's where you should be using abstractions. Here's like where you should try. Like formal specification languages in general, there's just not been enough use for us to like be able to like look at how everybody's using it and like figure out good rules of thumb. So right now, these days, it's mostly just people like running entirely on experience. There are some things we know. For example, if you're having if it's taking like forever for your model check, it might be because you're being too detailed. But like, again, it just really boils down to like expertise. Not a fun answer.
Okay, yeah, but it's mostly what I expected. So I'm doing my PhD in formal methods, and I thought maybe you have some from the practical perspective, some insights on.
Oh, sick. I would love to talk to you more about that. I want to keep questions moving, but like if you want to chat with me afterwards, sort of share with you my personal experiences.
Okay, thank you.
Mm-hmm.
Okay, cool. Vincent has a question. Would you like to unmute Vincent? Okay, so maybe Vincent cannot unmute.
I can read the question. The question in chat is, on which basis do you choose between TLA plus and Alloy when having to pick a formal verification language? My understanding is that the former is stronger in the behavior aspects of things. So again, mentioned Alloy is a different formal method that I also use quite regularly. It follows a different like lineage. It focuses on different things. The main advantage of Alloy is that it has a much nicer user experience. Like it can not only like find counterexamples, it can find examples, then it can give you like visual diagrams showing like the example as a nice laid out graph. Generally, I'm actually working on a post about this like in more detail, which I hope to have up in the next couple of months. Basically, the rough rule is that if you need like deeply nested data structures or like a lot of concurrency, TLA plus is way better. Alloy tends to be better if you're working with like static systems or conceptual maps or like things you want to give to like or things you want to be able to give to like project managers or like stakeholders that aren't like technically oriented. I really need to like write this full piece because there's also like a place where both of them overlap as both being good, but yeah.
Thank you. Are you done?
Yeah.
Okay, Evgeny has a question.
Hi, thanks for a great talk. It's helped to better understand TLA plus. So one thinking related to the question somebody asked about, is it only for distributed? How about GPUs, which is massively parallel multi-threaded devices, but with shared memory? Do you think it can be helpful somehow to validate programs there?
Can you give an example of a problem in GPU
I think
algorithms?
like one of the examples you can have like producer consumer problems. You have some parts of the system producing data, other consumes. They all operate through shared memory, basically main GPU memory.
Mhm.
It's kind of, there's a lot of massive parallelism, but more like fine grained rather than at the level of like I would say when you have many nodes independent from each other connected through some interconnect. But it's, you can scale it further for.
So I want to say, before I say anything, that major caveat to what I'm going to say, I don't know anything about GPU algorithms. Take everything I say, like do not trust anything I say. I'm not qualified to give an answer. I'm going to give an answer anyway. One of my favorite demonstrations of like TLA plus is like Decker's algorithm, which is a hardware algorithm for sort of like enforcing mutual exclusion between two threads where you don't have any kind of like compare and swap or like high level atomics. So the points of concurrency are literal like CPU instructions. Every CPU instruction is another point where like interruption can happen. And like I've shown like cool demonstrations with that where you can actually like model complex like systems. So there is like the viability to like model very low level algorithms. The problem I'd be worried about is either state space explosion where you have just so many possible states, like it takes months to like check, as well as like the fact that TLA plus just really doesn't handle things like floating point or like decimals at all. But I don't know how much that would be an issue.
Okay, that kind of helps.
Yeah.
Thank you.
And again, there are almost certainly, honestly, like I'm kind of wondering, there's this one guy, I think Alistair, like I follow him on Twitter, who's like done a lot of work in like verifying CPUs with like other tools. So I know there's like work with verifying CPUs. I don't know enough off the top of my head to give you a better answer than that. Alistair Reed, I'll put it in the chat. Yeah. I probably typed out his name, but you can look at him and he might be able to give you a better answer for formal methods in general, not necessarily TLA plus.
Thank you.
Thanks. Aaron, you have a question.
Hi. Yeah, so I've been trying to use TLA plus for a little while, and so I have a couple of specs I'm working on, and one of them is just exploding in state space, or it's running an infinite loop. I'm not quite sure which. Haven't been able to figure out what's going on. What are your recommendations on how to figure that out?
So basically what Aaron is asking about is what's called an unbound model. Because like TLC is a brute force model checker, what it does is it explores every possible reachable state. So if it turns out there's an infinite number of reachable states, usually because you have either an counter that's forever able to increment, or you have like a sequence that can forever like append, or you have a an infinitely nesting structure, you end up with an infinite number of states. Generally, one of the things that like is good is to enforce what's called a model invariant that says that like anything that could be like unbound is bounded, and that gives you an error that's a sign that things have gotten like out of hand. The other thing, and this is more of like a trick, is that basically TLC provides runtime statistics, right? So it gives you how many states it's found, how many are on the queue, and one of the things it gives you is the diameter, basically how many, the length of the longest behavior trace it's managed to find. If that suddenly balloons up really high, that's usually a sign that you have an unbound model. It usually, like in a better performing model, it'll usually like expand very slowly.
See, okay.
Yeah.
I'll take a look at that. Thanks.
Well, and finally, if you want, what you could do is you can use a dump parameter to just dump like a subset of the state space and then inspect it in like a graph analysis tool like Gephi. If you have an unbound model, you'll sort of see like long chains of like behaviors that just aren't connected to anything. But that requires like using a, what, sorry?
How do you do that?
You basically pass the dump. There's a dump parameter for TLC, and then you have to do like a little fix up because it doesn't necessarily produce valid graph is. Then you import that into a tool that I've used called Gephi, and that gives you a view of the entire like state space as a graph. And then you can sort of see if it has like really anomalous properties.
Interesting. Thank you.
Yeah.
Thank you, Aaron. Ted has a very nice question, actually. I'm quite interested in this myself. Do you want to go ahead and unmute Ted? Three, two, one. Okay, Ted is asking, can you please speak about your work and current consultancy engagements?
Okay, so I felt like, so I do like formal methods, right? But I am really, really passionate about teaching. And I have a very strong opinion that it is easier for somebody else to learn TLA plus to level than for me to learn their problem domain. So with that in mind, I mostly focus on two things: running workshops for like companies and the public, more the public now that the pandemic's happened. And those tend to be 3 days things where it's basically 4 people entirely on games. So entirely group exercises, labs, like hands-on things, discussions, and like actually applying it to like real world systems. The other thing I tend to do a lot of is pairing, where I basically work with a person to write the spec with them. So that way they learn how to write specs better and eventually reach a point where they don't need me anymore. I have done like also things where I just straight up review specs for other people. But that's like been less common. Those are the main things I do like professionally. Does that answer the question? Did you want to hear a bit more?
Ted can follow up in the chat, I guess. I actually have a follow-up question myself. I'm just curious how this normally works. Do you encounter resistance, or do people tend to reach out to you and they kind of are already sold on the idea, or you have like a champion within a company?
It's usually a champion within a company. People like a champion reaches out to me and is interested in, sort of gets other people on board. Is the main way it goes, because like, again, if I've not ever had success, and I don't expect I ever will have success, just enforcing it top down, like where manager forces people to learn it, that will like never ever work out. But when people like in the company like want to learn it and there's like alignment with like the managers, that seems to be pretty successful.
And have you encountered resistance? And I'm just curious, you know, in advance, like if I wanted to bring this to my company, like what kind of resistance might I expect to encounter, and how would I deal with it?
It'll probably be 2 categories, the resistance. One is people not understanding what it is. They'll think it's sort of like testing or like property testing or fuzzing, in which case a very quick way to solve that is with a demo, like basically just demonstrating what it actually does to like inform people, and people tend to really like seeing the demos of this stuff. Then the other form of like resistance is that it is basically too academic or like not going to actually find useful things. And what's happened, I've noticed, is that when people have actually like individually learned it and applied at their company and found bugs that way, that gets people on board very quickly. But that's pretty rare because, again, that requires a person to independently work on it for a while. And then, of course, the final resistance is we just don't have the time for this. We don't know where we'd fit in the schedule. And there's really no way of handling that. That's fundamentally a team and like management issue, not a tooling issue. Okay,
that's good advice. Thanks. I always assume I have to do everything myself anyway. Like prove it is the only thing you can really do.
What I really need to do is like make a video demonstration where it's just like a 5-minute video, like walking through a spec to show how it finds an error. And I mostly just not done that because I don't know how to record anything. I have a script somewhere for it.
Okay, Joel has a question, but no mic, so I can read the question. Has there been any work done on generating spec compliant executable reference implementations from TLA plus specifications?
I've seen some work done on that. Not a whole lot, for 2 reasons. One, it is a very, very hard problem. In fact, one of the reasons why TLA Plus and other tools have been so successful recently is because they basically try not to do that. When you try to sort of do that thing where you keep like the 2 things in sync, it just becomes so much harder to write the spec and prove it, which sort of slows people down economically. It makes it less economical. The other issue is that like I've seen some people do it, but it's very usually like tailored to their specific project. For example, one thing I've seen Netflix do, and they have, I think it's Netflix or no, it's Elastic, has a spec where they literally wrote a TLA plus spec that is so detailed that like it maps line by line to Java code. And then they basically just wrote the Java code line by line to match the TLA plus spec. And I imagine they probably use generators to keep those in sync. One thing I've seen that's happened with more success, but again, very like local to the company, is using TLA plus to generate tests for the code. Yeah. So, does that answer the question?
This kind of refers back to your waterfall is not that bad. I wasn't sure if that was a joke or not.
It's like 85% of a joke. It's My standard opinion, so if you actually look at if you look at the history, Waterfall was never actually that big. It was big in small circles, but basically most people followed either one of two things. They either followed an ad hoc process or they followed an incremental process like V or Spiral. Waterfall mostly became like large enough popular consciousness from two forces, one being the rational unified process in the 1990s, and two, Agile defining itself like against the Waterfall like movement. Waterfall as it like originally is conceived is actually really bad for like, and that's the reason everybody used an incremental model instead. I think the bigger problem with like modern development is that they've gone so far in the opposite direction of not having any upfront planning at all that it causes issues. So like Waterfall's bad, but like upfront planning actually a really good idea.
Okay, Barasari, I'm sorry if I mispronounced your name, but go ahead and unmute and ask your question.
Oh, hi. Hi, Hillel and Stephen. I'm quite interested in TLA plus, formal methods, functional programming too. I actually, the problem is I can't find enough time, right, to learn enough of these things. Like, to say the persistence at work, we don't have time for that. And it's how. So if you want to go deeper, you need a more mathematics background. So what kind of mathematics background do you think will be helpful, like as a minimum to get very effective at this when I start learning this?
Okay. So by far the most important, in my opinion, like the most important like mathematical discipline to understand all of this is predicate logic. Predicate logic is basically like Booleans over sets. So you have the ability to sort of say something is true for every element of a set and something is true for at least one element of a set. I did a tiny bit of that in like the thing. The reason I recommend predicate logic is twofold. One, it is relatively simple to learn. Like there's only like a couple of like stumbling blocks for most people. And two, not only is it very important to understand formal methods, it is really valuable to programming in general. Like you can use it to do things like case analysis, given a bunch of like parameters. Is there any like cases we've missed or have we gotten them all? It gives you things like the ability to like write properties of things really well. Like a sort should have the property that for every two elements of the sort, if the index of one is less than the index of the other, the value of one is less than the value of the other. And once you can express properties of things, it becomes a lot easier to do any kind of informal design, do any kind of property testing, figure out types, use formal methods. It's honestly one of the biggest bangs for your bucks you get from math, and also is good because it ties into formal methods really well. I've not been able to find like a really good like introduction to predicate logic format for like programmers, which sucks. And I might just have to write it myself, but it is just one of the best tools you can learn. Like, yeah. Does that answer your question?
Yeah, that does. Helps. Thank you.
Welks.
Okay, there are no more questions in chat right now, and we're just about at the 1 hour mark. So why don't we stop the recording and maybe we could just have a few minutes afterward, casual chat, say hello.
Mm-hmm.
So I just want to thank you again for joining us this evening, Hillel. This was terrific, as always.
Thank you for having me.
It's kind of fun seeing you pitch this concept, and I hope everyone got something out of it.
Thank you for having me, and I'm glad you all enjoyed.